Remember the negative sign, remember Lenz's law. It's not going to just allow that current to pass through without pushing back. It's going to push back against that. And so in essence, by pushing back, it means that there's going to be an induced voltage. That end's going to be high and that end's going to be low. Because it's going to try to oppose that current going into it. Current doesn't want to go toward a high voltage spot. Current wants to go to a low voltage spot. So this is how that induced voltage winds up being oriented. And so as we go across that inductor, we lose voltage. And how do you calculate that for Ohm's law for an inductor? It's L, 3T. And then there's current flowing through the resistor minus IR equals 0. Well, those two equations look totally different, but I can make them look the same. I'm going to take every R in this equation and change it to an L. I'm going to take every Q in this equation and change it to an I. I'm going to take every 1 over C, change it to an R. If I do that, let's rewrite this equation with those red quantities. I'm going to leave V0 alone. So this equation becomes V0 minus I. Well, what happened to I? I didn't say what happened to I. Well, let's see. Q went to I. How does Q relate to I? Time derivative. So Q got differentiated and turned into I got differentiated and turned into dIdt. Going this way, we will get electrically, that's a derivative. Because Q got differentiated and turned into an I got differentiated and turned into an I. Guess what? Electrically, changing from LR to RC does. Just take a wild guess. You can do calculus with electric circuits. Okay, I goes to the IDT, and R goes to L, and Q goes to I, and 1 over C goes to R. And you see, if I make these changes, these substitutions, I can turn this circuit into that circuit, or I can turn this equation into that equation. Does that make sense? I hope it does. It's a pretty common technique that you learn one system and then some simple changes can teach you about another system. Well, with that then, I'm going on to slide 15 now. With that, I'm just going to remind you that the, quote, answer to our RC circuit, when we solved that back in an earlier chapter, chapter 24, no, it's chapter 26, we found that Q was equal to C V0 times 1 minus U minus T over RC. That was the solution to this equation. Let's write the solution to the inductor equation then. It's going to say that I equals, that's right, Q's become I's, C's become 1 over R's, V0s stay V0s, 1 minus E to minus T over RC. What would RC be? R goes to L, and C goes to 1 over R. R goes to L, and C goes to 1 over R. And there's the answer to that circuit. That tells you how the current behaves in time without having to solve anything. I sometimes facetiously call this trained monkey physics. Because if you can train a monkey to take every RC circuit and make these substitutions, they'd have the answers without understanding the physics. That's one way you can think about this. In our RC circuit, we found that the current, which was the derivative of this thing, was C times V0. Well, if you do the intermediate, I'm just going to give you the answers. You can go back to the previous chapters and look this up. Turns out to be that. Well, what's that mean over here? It means that di dt. Now you can differentiate this if you want to. But you can also do trained monkey physics. Di dt turns into V0 times C. Let's see. V0 stands on C. No, R goes to L. Sorry. V0 L. E minus T over R. I'm going to choose one and see if I did that right. Oh, that was over R. It should be over L. You want to pick up the bottom of the screen, did you think?
Mm-hmm.
Showing up okay. All right, hopefully it is. Now, what did C tell me? Sorry, what did Q tell me? Tell me how much charge, but I could also find out the voltage on the capacitor. The voltage on the capacitor is Q over C. This is V0 minus E minus T over C. What's this tell me? The voltage across the resistor, which is IR. The voltage across the inductor is L di dt. It's going to be V0 times E to the minus 2 over C. So far, we can develop all these relationships. Why don't you pan to the screen? To the whiteboard. No, I'm sorry, the screen. So there's the result of doing this. You may have to go back over this a time or two to see what's going on, to remember that. I don't ask you to derive this, I just want you to kind of understand it, that you can start with the RC circuit and get the LR circuit. Or you can go backwards, you can start with the LR circuit, go to the RC circuit. And while she's still got it focused up there, I'll just remind you that we had a time constant for this RC circuit. That was R times C. Remember what that time constant told you? It told you something about the speed at which this circuit changes. It's a similar thing for the LR circuit. There's a time constant. RC becomes L over R. RC has units of seconds. L over R has units of seconds. So you can just leave that on the screen for a bit. If you were sitting here in class, I would now pass out a piece of paper. It's printed on both sides. It's called the capacitor inductor summary. And it's got everything that we just did about LR circuits. It's got the two circuits, the Kirchhoff's rules for them, general statements about them, graphs about them. I'm going to show it to you here on the screen. Here's the front side of the capacitor inductor handout. Stick on my point. A few things. So there's our RC circuit, there's our LR circuits. Here's our loop rule. Here are our results. Energizing the inductor, same as charging a capacitor, storing potential energy. And there are the equations that govern what's going on. By the way, you can take these answers, plug them back into this equation and see that it works. Remember doing that? On the RC problem on test 2, I had you take equations like this, plug them into a differential equation, and show that it really worked. Now with that capacitor then, we could flip this switch, take the battery out of the circuit, and discharge the capacitor. Here's the equations we developed for that back in an initial chapter. We can do the same thing over here. We can flip this switch and de-energize the inductor, get that potential energy back out of it. Same thing, we can duplicate ideas, come up with that. Some general things, time constant, RC, time constant L over R, potential energy expressions, we've already talked about those. Energy density expressions, I've already talked about those. Remember some circuit analysis things that we talked about for RC circuits? They start out as a short and they end up as an open. Inductors behave just the opposite. They start out as an open and they eventually wind up being a short. And then these other statements down here about AC circuits, we'll get to that later in the chapter. Here's the back side of the capacitor inductor sheet. It shows you pertinent graphs. It reproduces the answer equations. Looks like I'm missing an equation back on the other side. See that hole right there? I think it should be that. It looks like I just never finished the front side of that. Here are the graphs. Charge of the capacitor, the voltage across the capacitor, asymptotically approached the battery voltage. Or the charge, asymptotically approaches full charge, the current decays. For an inductor, the current builds up. And then there's the corresponding discharging. I'm not going to have you do a lot of this in the homework. I don't have you do hardly any of that on the test. But if you were here taking the test, instead of at home taking it, I would hand you this capacitor inductor sheet and say that's fair game to use on the test. So these two things from the PowerPoint slide, and they are also, I'll show you where that is, if you're here in Blackboard, in the chapter 30 section, of course there's the slides which you're using, but down here someplace, there's the capacitor inductor sheet. So at any time, you don't have to dig back through the PowerPoint slides to find it. There's the capacitor inductor sheet. You can always just download it from Blackboard and have the same thing. Right here, available for reviews. Ah, this one doesn't have the hole in it. And that's good. I must have fixed it eventually and just didn't fix it in the document that's in my slides. My slides are older. Okay, back to my PowerPoint. We're just about done with this lecture, which is good because it's been 51 minutes or so. I haven't seen time not too bad. Here's a summary of what we've done today. An LR circuit relates to current the same way an RC circuit relates to charge. So again, there's that differentiator thing. How do you get from charge to current? You differentiate. So you differentiate an RC circuit, you get an LR circuit. You start out with something at 0 and it builds up to an asymptotic maximum. What's in the charge of capacitor? I write a statement down here that's from a previous chapter, and I just, trained monkey physics, change the words. Charge into energizer, capacitor to inductor, charge to current, capacitor to inductor. Discharge. So you can read through that. I don't have to read that sheet to you. Okay, well, yeah, this must have been the perfect lecture because there wasn't a single question the whole time. This is amazing. I guess I'll get better with this age. All right, well, there's an MIT video that goes through a lot of this as well. You can listen to somebody else talk about this instead of me. And of course, now that you have this video, you can go back and forth and find things that you need to listen to again and so forth. But I think we'll stop here. So this is the end of the first lecture for chapter 30. Hope you guys are doing well. See ya.